Okay, so before we talked about safety today, which is our last subject to wrap up before we go into another big area, which is three-phase. But before we talk about safety, I wanted to talk about laboratory number 3 that you're going to be doing this week. If you've read ahead in laboratory number 3, it says that, and are both monitors up there? Is that working? Okay, great. So laboratory number 3 says that before coming to lab, come up with an expression for this part of the circuit over here. The source in this resistor is really just for safety. But for this part of the circuit, so that we can get the power factor as a function of the variable resistance Rx. This is going to be kind of a fun lab. If we look at the oscilloscope, you're going to have a couple of waves on the lab, and they're going to be out of phase. And we're going to actually, by varying this resistor, this is going to be a variable resistor. That'll be a potentiometer. Remember, you just use the middle lead and one of the outside leads to get that potentiometer to work. We're going to be able to take one of these waves and shift it back and forth. Because as you could imagine, when current gets here and has a decision which way it'll go, if this is less resistant, you're going to have more current going through the inductor, which means this circuit is going to look predominantly what? Inductive, right? Whereas if I reduce the resistance here, then more current is going to go through the capacitor and the circuit will look what? Capacitive. Now you can have variable inductors and you can have variable capacitors. That's not a problem. But I tried to keep this easy. We're just going to use fixed value inductors and capacitors and change which way the current goes just by changing the resistor. Now there's a couple things that I did with your circuit. I put this resistance R2 here, I think, as a fixed value, but I know good and well that you're going to have a lot of resistance in that inductor, so that's going to be a nice place to put that. Because you'd hate to go through this calculation and come up with a really nice equation and then get down to lab and go, oh yeah, I forgot, the inductor has a lot of resistance, where do I put that? Well, we now have a place to put that. You can just tack it into R2. So I think on the diagram you see R2 is probably 100 ohms. When you get down to lab, you probably throw another 500 ohms in there with it to account for the resistance of the inductor, whatever you measure that resistance to be. Then the other thing that I'm going to do to keep life easy is I'm going to take this R3 and combine it with Rx. When you build it in the lab, you will build it with this R3, but for calculation purposes, I'm just going to take this R3 and this Rx all as one. Okay, make my life a little easier with the calculation. So what I'm going to do is I'm going to come up with the impedance for this part of the circuit, which is just two parallel branches, right? So I could say that that's product over sum. I could say that I have R2 plus J X sub L times the product Rx plus J X sub C. And I've defined X sub L as omega L, and I've defined X sub C as minus, so I put the negative there, 1 over omega C. Now, if you want to define X sub C as positive and put the negative up here, that's fine. That's your prerogative. I'll leave the negative down here so I don't have so many negatives in that calculation. So I have the product in the numerator. I have the sum, the reals, R2 and Rx, and then the complex, X sub L and X sub C in the denominator. Well, I could keep working on this, and at some point I'm going to bow out of this and let you finish it up. But let's see, I would have R2 times Rx plus J R2 X sub C plus J X sub L Rx plus J squared XL XC. Is that right for the numerator? And then I will have R2 plus Rx plus J X sub L plus X sub C. And looking at this numerator, this is real. I'll use a lowercase r. This is complex or imaginary. This would be complex. And this, remember J squared, that's minus 1, isn't it? So with that being minus 1, this becomes real, doesn't it? So if I were to group reals and complex in the numerator, I could say that I have R2 times Rx minus, is this J squared, XL times XC, so that's the real portion, plus j times the complex portion is going to be R2 x sub c. Is that right? R2 x sub c, yep. Plus x sub L Rx. Okay, and then I am still dividing this thing by what? R2 plus Rx plus J XL plus XC. Everyone's okay with that? Now I think I'll write this impedance as equal to some magnitude at some angle theta. And quite frankly, I don't care what the magnitude is. I want the angle theta. So I could write this as some magnitude at some angle. What's that angle going to be? Was there an angle for the numerator? Of course. It's going to be the arctangent of the imaginary portion, which is R2 x sub c plus x sub L Rx divided by R2 Rx minus x sub L x sub c. And then is there an angle for the denominator? Yeah, and what do? We subtract those. And we're going to have x sub L plus x sub c divided by R2 plus Rx. So that's theta. And why am I interested in theta? Because the power factor is equal to the cosine of theta, right? So I'm very close in coming up with an expression for the power factor as a function of Rx. Okay. Did I do my math right there? Let's see, I should have that one, R2 x sub c plus XL Rx divided by this one, R2 Rx minus XL XC. And then we're subtracting because of division. That's where this negative comes from, because we're dividing. Complex. Yeah. Now, if you're wondering, well, how do you pick the numerator and the denominator in the arctan function? Remember, if you go to your phasor diagram where you have the real and the imaginary, okay, and you have the, take a number like A plus JB, you come over A, you go up B, and if you want to find this angle theta in here, what's that? Arctangent of the opposite, which is B, over the adjacent, which is A. Okay, so I'll leave that like that. There's a little bit of finishing work there. Probably the biggest thing you want to do at that point is to put it into your calculator so that you have something you can use down in laboratory. Or remember, we've got computers down there with Excel. So you build a function in Excel and you can use it down there, because you're going to want to be able to come in and define what these resistances are and what those inductors are based on what you measure in lab. Run your calculations and see if that coincides with your actual value of Rx. Yes?
This one in the reference order inside the involved expression, is that XL plus XC over R2 plus Rx?
Mm-hmm. Yeah. You're going to have this term in the numerator. You're going to have this one in the denominator. Okay. So questions of that? So make sure you look at that before the laboratory. The laboratory can go pretty fast. If you have this done, you can come in and be done with the lab in about 20 minutes. The other option I usually see, or sometimes see, is students that will spend about an hour or 2 hours and 20 minutes working on this, and then they'll do the lab and go, oh, this would have been really easy if I would have done this before coming. Yeah, it would have. Okay. So, questions of that? Well, what I wanted to spend some time today doing is talking about safety At the beginning of last term, we talked about some safety things, and we just said, do this and don't do that so that you'll hopefully be around to get a grade in the class. We probably weren't prepared to talk about the practicalities of that. Why do we do this and why don't we do that? But now we've had some study and we can actually do some calculations and recognize why we have to be careful. We might reiterate that we do have to have care. If I were to look at the current spectrum, so I've got current here. Okay. I've got current, and as I start out at low values, and you'll find a spectrum like this. Your author may have it in a textbook or something. If you go online, you can see a spectrum. But at 500 micro, so that's 10 to the minus 6. Whereas milli, 10 to the minus 3. So at 500 microamps, that's the UL limit for consumer products. Not medical products, and certainly not products that are attached to the body, but you got a lamp or something, that's the limit there. We know there's not any perfect insulators, so that you always have some current leakage, and that would be the limit. About 600 microamps is imperceivable. Most people can't feel it. At about 5 milliamps, so we've gone to 10 to the minus 3 now, milli, you've got pain. Remember, we first talked about you can electrocute someone with about 10 milliamps. Okay, there's 10 milliamps. So that's where we go from pain to 20 milliamps where you can't let go. This is where things get real dangerous. Maybe you've heard of someone that's got shocked or worse yet, electrocuted, and they couldn't let go. Okay, that's when you get into big trouble, which is probably another reason that we never let you work alone in the laboratory. You always want to have someone there to try and turn things off and to render aid. Then we go to 100 milliamps. That's the most danger. That's a transition where you can't let go, where your heart's going to stop, and that. So that's the most dangerous. That's maybe we should rewrite this. This is equal to what? 0.1 amps, right? 100 milliamps is 0.1 amps. Just to let that sink in. About 1 amp, your heart stops, but if someone is there to render aid, turn off the electricity and restart your heart, you could have survival. About 10 amps, then you start transitioning into real burns and problems like that, where if you burnt vital organs and things like that, you're going to have some real problems, but you can survive it. But in this region, this is the most dangerous because you have the combination of your heart stopping and you can't let go. You got real problems in there. So you want to avoid that. And certainly be respectful. It doesn't take much to get 1/10 of an amp. Okay. So what are some precautions that we talk about? We talk about treating all circuits as potentially dangerous, right? We try to develop good habits in labs, so when we do work on dangerous circuits, I think our laboratory number 4, you're going to be working on 208 3-phase. Most of it will be dropped down, but at some point there'll be 208, so you have to be careful of that. You have real problems with that. You have to start thinking about the practicality of where you get shocked. Across from one hand to the other hand is usually the worst possible combination because that takes current across your chest cavity, across your heart. So holding on to something that's grounded and then using a test probe or something to measure something is really quite dangerous. A lot of times technicians will get in the habit of grounding their elbow. So they'll make a conscious habit of not holding on to anything with the other hand to avoid that path and then ground the elbow. So if you do happen to slip on the probes or something like that, the current path is from your hand to your elbow. So you could have problems, a lot of pain, burns, and things like that, but you're protecting your heart. We always say, well, don't work on electric circuits when they're energized, and then we turn right around in the next sentence, or maybe when we use a semicolon, put it in the same sentence, measure voltage V, okay? You can't do that with it turned off, can you? So if you have to make measurements with the circuit on, use caution. Make sure that the equipment that you're using is right. If you're measuring a 5,000 volts, should you use the ohm meters that we have, or the voltmeters that we have down in lab? Anyone check to see what those are rated for? Usually about 600 volts. Okay. You also have to make sure that the probes are rated for what the meter's rated. The meter might go to 2,000 volts, but usually the probes only go to about 600 volts. You start going above 600 volts, you got to spend a lot of money. And I'll bring some examples and some equipment in. Some other things that we've talked about: capacitors hold charge for a very long time. So if you're working with something that is a capacitor, there's going to be a protocol to discharge that capacitor so you don't damage the equipment, so you don't hurt yourself. You can have significant heat in electrical equipment, so you have to be careful of that. One thing we talked about too is if you go to render aid for someone that's in an electrical emergency, a lot of people, it's their inclination, they want to help someone, but going up and touching the person, that's the worst way to help them, right? What do you want to do? Yeah, turn the power off. We've got the emergency shutoffs in lab. You could simply unplug the device if you're at home or even in lab. If you can't do that, you can't get the disconnect, then plan number 2 is what? No one's got a plan number 2? Okay, cut their hand off. All right. Yeah. You probably want to try and move them away from being in contact with something that doesn't conduct electricity. Well, that would be good. A fiberglass shovel handle or a wood shovel handle, that's going to protect you to several hundred volts if it's a nice dry wood. So some things like that. An old beer bottle, I don't know, whatever you can find around. But the big takeaway from that is you don't want to rush over and grab onto them, because you will become victim number 2. So be very careful with that. Some other things, and we'll talk about along the way, is electrical fires you have to be careful of. You certainly don't want to use water on electrical fires. And then there's the whole thing of arc flash, the energy of the vaporization of the materials and whatnot. So we'll mention that before we wrap up this section, and things to think about. Well, in wanting to try and get some calculations, we probably need to look at the resistance of the average body, and you'll notice on these numbers that I put the approximation symbol. So the resistance of dry skin is about 15,000 ohms. This is a K ohm, so don't let that get past you. Whereas the resistance of wet skin is about 150 ohms. This is where, again, if you have to measure the voltage on something with the circuit energized, you want to be careful. You don't want to be standing in a puddle of water, right? Because this is a huge difference. This makes it very easy. As this goes from 15,000 ohms to 150 ohms, it makes it very easy for current to enter your body. Okay? And, something you got away with, or you heard your uncle got away with yesterday or last week, may not work for you, because you might have different resistances, and maybe someone else had dry skin, and you now have wet skin. So a lot of times when we lay out these rules or we do some calculation, you say, well, yeah, but I've heard people living through this. You have to be careful, because you could be having a bad day, and you could be, instead of up here where the person was able to get away with it, and be down in there. Once the current gets through your skin, it is relatively low resistance in your body. An arm or a leg is usually about 100 ohms. It depends. This depends on your physiological makeup and whatnot, and size and whatnot. But about 100 ohms. The trunk is about 200 ohms. So let's put some of these numbers into play and look at an example. Let's say that we have a electrical distribution system like you might have here in this building or at home. So we have some source, and then we'll put some sort of a breaker in it, or I'll say a fuse here. And a lot of the plugins in this building would be 20 amps. At home, you probably have a lot of them that are 15 or 20. So we'll just say 15 to 20 amps. I don't think it's going to matter. And maybe then we'll have a motor here. So we have some resistance, and we got a whole bunch of inductance. That's our motor. And it's coming back like this. And maybe we've got it in a metal case. All right. And you're hanging on to it here. Like that. And I guess you'd be grounded, wouldn't you? Literally and figuratively. Okay. So you got something like that. So everything's good. You got the old drill or circular saw or vacuum cleaner or whatever. You're doing a lot of work. Everything's going great. And then all of a sudden, you have a fault. Okay? So you get a fault in here. You might say a short. Okay? So you're working so hard, a drop of sweat gets in there and shorts from there to there. Or maybe it's a cheap product and the winding burns out and comes over and flops over there. Or maybe you drop it in some water and it shorts from there to there. However, but you've got this fault or you've got this short from there to there. So now what's going to happen? Well, some of this current that was going through here could go through you, right? Not a good scenario. I mean, you could say, well, I got dry skin, but you add this up, and you've got a problem. You could have some current going through you. And we saw that it doesn't take much current to electrocute you. Certainly, is this going to keep you from being electrocuted? Is there a question over there?
Well, when I was a kid, my grandparents had a VCR that hung, and if you touched it, the whole arm would tingle. So do you think that was probably what it was?
I'd probably not touch it. So yeah, you can. There's all kinds of scenarios. I was in a pool one time with a light that apparently had a problem. And as you swam closer and closer to you, it would give you kind of a tingly feeling in the water. And so we used that as an opportunity to see how close we could get to the light. But that probably was not that good. This can manifest itself in all different areas. Yeah. Well, I don't. You know, those probably won't kill you. This you could have a bigger problem. Because I mean, if we look at this current here, this circuit breaker that's down in the utility room or the power distribution center is 15 to 20 amps. Is that going to keep you from getting electrocuted? No, I mean our numbers up here, 15 or 20 amps. Yeah, it'll just cook you, no problem. So what are the circuit breakers for? What are the fuses for? This protects the wire. So if you get to work in that wire too much, you try and demand too much power through it, or there's some short onto itself, then it will trip. It's not there to protect you. You'll be dead a long time before it gets tripped or blown. So what we do here is we will hook this thing to ground. Okay? So we take a nice clean copper wire and we hook this to ground, and the resistance here is about 0. Nice clean copper wire going to ground. So now we have this fault and we have current. So is current going to get to this point and go through you, which could be, depending on dry skin or wet skin, you've got a foot and a hand in there. You have several hundreds to thousands of ohms, right? Depending on how wet your hand is, how wet your feet are, and things like that. So which way is the current going to go? Is it going to go through you with hundreds or thousands of ohms, or is it going to go through this copper with really virtually no resistance? Yeah, it's going to go through the copper, and that's then going to cause the current to increase and actually then open this up, right? Okay. So this is why when you're looking at a circuit, you have 3 prongs. If you look at the plug-in, you have the 3 prongs like that. This is the hot one. So this is the hot. This is going to be the common. So there's the common. And this is going to be the ground. Okay. Will the appliance work without the ground? Yeah, you see a lot of people, they cut the ground off, okay, for some reason, because it won't plug into an old style plug-in or something, but they cut the ground off. And it will still work until you get a short or a fault in there, and then what's going to happen? You're going to have problems, right? Because when you cut the ground prong off here, you essentially open this up, and you're inviting trouble. Okay. So we'll talk about other ways to deal with this. There's GFIs, ground fault interrupts, and things like that. We'll talk about that, and we'll do some examples when we get together next time that will hopefully make you a believer in all this. So that's where we'll go.